Now I would like to start my main part of the presentation today. The title is called the deployment of EMC compliant IC chip techniques in the design for hardware security. This is the outline of my presentation today. So I will start with some introductions. Especially talking about what's electromagnetic compatibility and how we see the relevance to the hardware security. From my side, the electromagnetic compatibility is one of the major topic in the sense of safety of the hardware. And the security side, of course, that we will talk about the attack resiliency on the hardware. And also I will talk about the power noise simulation technique. This is a key technique to make some analysis on the electromagnetic compatibility of the integrated circuits. And we will apply those techniques to the side channel leakage analysis from the hardware security point of view and draw some conclusions in the last. And I would like to especially give the students about the terminology and some ideas and in the background of those things listed here. So the first, this is a snapshot of the EMC. I think you may have the image of the electromagnetic compatibility in the measurement site, anechoic chamber like this. And in this particular case, we have a car here. This is a real EV, electronic vehicle. And the antenna is capturing the some radio waves radiated from the electronics in the car. And at the same time, that antenna can inject some electromagnetic disturbances onto the electronic components of the car. The interactions, bilateral interactions, we often discussing in the framework of the electromagnetic compatibility. So one word is the immunity. How the radiated and the conducted disturbances will be interfering with the internal operation of the electronic devices, even in the car EVs. And at the same time, what kind of the EM radiation will be coming from the car. Sometimes we call it EM interference, EMI. So both EMI and EMS are in the bilateral or the both sides of the problems in the EMC. So I think this is the image. So today I would like to connect those images. Obviously, this is the area of the EMC, but those ideas or image can be translated into the security side, security aspect of the integrated circuits. Let's go going into the details of the EMCs in the circuit design or circuit characteristics viewpoints. I think some of you may know we have the standardized testing technique on the EMC of the IC chips. Now, one is the magnetic probe. This is the measurements of the emission of the electromagnetic waves from the IC chip under the operation. Sometimes the frequency range from 150 kilohertz to the 1 gigahertz. Of course, that this frequency of interest gets wider in these days. And also, on the other hand, we have the direct RF power injection method. Sometimes we call it RF-DPI for the measurement of the IC chip immunity against the electromagnetic wave injected into the device in the same frequency range. Of course, we have many other types of the standardized testing methodologies as listed in the IEC table shown here. Those are basically the techniques used for the product designs in terms of the EMC compliance. But again, that those techniques can be quite useful in the sense of the measuring the hardware security performance of the IC chips. So the students should learn those standardized techniques beforehand going into the area of security. So now, this is the image of the EMC. RFI, this stands for the RF interference. On the LTE, long-term evolution, which is one of the latest, the mobile cellular wireless communications, and undesired radio waves can interfere with the operation of the LTE. In this particular chart, I show you the horizontal axis gives you the frequency in the measurements, and the vertical axis gives you the noise level measured by the spectrum analyzer, for instance. And what the noises are. In this particular case, actually that we have measured the noise coming from the controller of the wireless power transfer system. This is sometimes we call it WPT, specially designed for electronic vehicle. DUT means that device under testing. In this case, that we are measuring the undesired radio waves from the controller of the WPT. And what's the distance? This is quite proximate to the this controller chassis, 0.1 meter, 10 centimeter away from the surface of the DUT. So this means a very proximate, very close positions. We measure the radiations. In the case where the WPT was off, we don't see specific tones or specific noise features, but once we turned on the WPT system, obviously we see many different frequency components as undesired radio waves. And those blue areas are the frequency zones which the LTE actually the system uses. For instance, in the frequency zone of the 840 megahertz or the 1.7 gigahertz or even 4.2 gigahertz, or depending on the nations or depending on the systems, but those three areas often LTE systems are using. So if you put your cellular phone very close to the surface of the WPT controller, because of those undesired radio waves, the interference happens, and sometimes your phone cannot operate correctly, or you cannot talk to the other people over the phone. This kind of the RF interference, this is the area of the research in the EMC. And but this is just I would like to give you some image of what's the EMI in the sense of the experiment, or in the sense of the academic research on the EMI. So because this is the observation results, but of course that we need to understand why the noise are coming from the front side panel of the WPT controller, and what kind of interaction happening between the noise with the front end circuitry of the RF device, and so forth. Another aspect of the EMC, in this case, that the EMS susceptibility or the immunity of the system are measured in the real device. In this case, CAN. This is the one of the wireline techniques used especially in the card or robotics environment. Horizontal axis gives you the RF frequency, and the vertical axis gives you the level of the power of the injection into the CAN in a specific DPI measurement setup. And obviously, if you put the big power onto the CAN transceiver, something will happen. Sometimes the wireline connections will be broken because of the incoming RF disturbance on the cables of the CAN. But we have some compliance or some regulations for the CAN IC chip to be resilient to the incoming power. This is sometimes sometimes we call it the mask. In this case, for instance, the RF frequency at the 10 megahertz, the power higher than 34 dBm. This is more than 2 watts. In this case, the CAN IC chip needs to be okay. So this have the good the robustness or the tolerance against the incoming power. Those the requirements is set by basically by the industry environment. And what I want to show you is in this case, even in the OK area, if you put some power, the RF of the 5 megahertz at the 34 dBm, the tolerance by definition in this case for the CAN is a delay variation within 200 nanoseconds. In this case, OK, the TX transmitted data is well received by the RX within the 200 nanoseconds. But obviously, we see some glitches here because of the RF DPI, because of the RF power injected onto the CAN device. From the system point of view, the data can be well transmitted, so nothing violated. But in the real area, in the real environment, we will see unwanted glitches here because of the RF DPI. In this case, we also need to have some way making the understanding of the what is happening in the circuits. What's the interaction between the RF power with the operation of the circuits? Very deep understanding or deep analysis or the scientific research activities are needed for the complete understanding of the interaction between the RF and the CAN. So those two, I just wanted to show you the image of the EMC, experiments. From now on, I would like to slightly change the topic to the hardware security. In some applications, obviously nowadays, especially for the IoT applications, the people are using the cryptography, try to make your data in a private environment, not to disclose the data to the other people. In that case, the data needs to be well encrypted by the nicely designed cryptographic engines on the IC chip. But obviously the adversary sometimes they are coming up and try to extract some your private designs from the operation of the cryptographic engines, unfortunately. And even in some case, the Trojans, hardware Trojans can exist within an IC chip. This is not always. It's a very kind of the scenario-based topic, but it can happen. So what kind of Trojans? They may try to disclose your design to the specific people unintentionally from the user side, but intentionally from the attacker side. Sometimes those things can happen with the knowledge of the electromagnetic interference or electromagnetic susceptibility. Why those can happen, I will show you. So as I mentioned that there are many types of the EM measurements. EM stands for the electromagnetic, and now from now on, I would like to use the EM. So if we have the chip, the size of the chip is typically like 5 millimeter or 10 millimeter or even smaller. And the EM can be radiated from the chip surface when the circuits are operating. And the antenna can closely come to the surface side of the die. But obviously, we have the board, printed circuit board. In that case, the antenna can scan over the older board. Or even in a bigger room, you can have the big antenna that can capture the EM noise or EM radiations coming from the operation of the die. So from the attacker side, the very wide range of the free space is given. So the attacker can put the antenna just on the die or scanning over the PCB board, or even on the room, they can put some big antenna or nice amplifier to extract the EM waves from the die. So it's quite easier for the attacker to capture the EM waves. If you design the chip, I think if you design the cryptographic processor, it's a digital design that can be situated in the center part of the die, for instance, and people who wants to protect the cryptographic processor from the attacker side, and so they may use power management control to isolate the power domain from the outside. Or they may use a PLL to provide the proper clock signal given to the processors, and also data interface should also be carefully designed. Those circuit constitutions can be quite helpful for the designer to protect the cryptographic engines from the attacker. But EM is quite powerful because even with those structures, even with this structure, the EM radiation can happen at the position of the cryptographic processor. In that case, the antenna can come to the position of the cryptographic processor, even those processors are protected by the PMC locally or PLL or data interface, but still the EM can radiate at the position of the cryptographic processor. And even worse, the active attack can happen. Active attack means that the EM injection can be placed on the position of the cryptographic processor. Because nowadays we have very tiny antenna, and that can be scanning over the die. And the specific locations, they can inject some faulty operations into the cryptographic processor. And then attacker can extract some secret information from the response of the cryptographic processor. I will show you I will discuss more in detail about the attack scenarios or attack operations. But the image here is that the attacker still have the good position. Attacker is always in a good position to extract some information. So now, one of the most well-known or the powerful attack methodologies is a kind of the power analysis. In this case, the attacker can extract or attacker can measure the EM waves from the die and try to make some analysis on the set of the EM waves to extract the secret information, just measuring the EM waves. In this case, the attacker may put the antenna over the die and make the measurements with the oscilloscope as shown on the right, and try to capture the sometimes more than 10,000 or even millions of the wave shapes during the operation of the IC chip, the cryptographic engine inside. This is exactly the image as I showed you in the previous slide. Even that the chip has many different types of the circuits, not just the cryptographic engines, but they may have the PLL, AD converters, and some other circuits. But the antenna can come to the location of the cryptographic engine on the IC chip, for instance. Once the attacker captures the wave shapes, EM wave shapes, they have the many different way of the analysis to extract the secret information. The number one, this is a simple power analysis. The number two, differential power analysis. Number three, correlation power analysis. And in some cases that we call the local EM analysis. This is especially the measurements done by the antenna to capture the EM. To show you what is going on the attacker side, so I will give you one video here. So here you see the chip here. The chip has the cryptographic engine internally, and here is a magnetic probe which is measuring the EM on the power terminal on the board, not on the die, but on the board. Here, I think here is the power terminal, and the magnetic probe is measuring the EM waves radiated at the position of the power terminal. And the output of the the magnetic probe is given to the amplifier and then going to the oscilloscope to capture the wave shape. So now I show you video here. Just a second. Okay. Here's the window of the oscilloscope, of an oscilloscope. Here in this green one is the measurement results. And in this left part, nothing is happening, but on the right-hand side, the operation of the cryptographic engine. And once we measure the wave shapes, we see some pattern here. Once again, okay, this is the second shot that I would like to show you more. Okay, I would like to stop the video at this point. You see, this is the measured wave shape, and we see the clear patterns like long, short, short, something. So long, short. Those patterns actually exactly match the internal secret key byte in this cryptographic engine. Of course, the design is not good in this case, but this is quite the obvious results of just measuring the EM waves coming from the die. You can see the you can extract some secret information from the using in the cryptographic engine. This is very powerful. I think you may imagine or you may consider some techniques that can reduce the level of the output, but it's not easy to completely eliminate those kind of the correlation of the noise with internal operation of the cryptographic circuits. Okay, so this was the one of the video I showed you. So from the previous slide sets, I think many people are now understand that EMI and EMS are quite relevant to the hardware security attackers scenario. So EMI, electromagnetic emission, this is a quite straightforwardly related with the side channel leakage. As in the previous video, the EM waves can be captured by the attacker and analyzed to extract some information. So the EM emission, this means that some information is leaked through the electromagnetic or EM waves. And also for the analysis side, if you are expert of the EMI analysis, those knowledge can be applicable to the side channel attack analysis. And for the EMS side, I didn't show you any the video on this, but sometimes the fault injection can also give you another way of analyzing the internal secret key bytes, just by analyzing what kind of the faulty output are coming out from the cryptographic engine. Because those faulty output can be created just by the intentional injection of the fault by using EM power, for instance. In this case, the EMS analysis, susceptibility analysis can be applicable to the fault analysis. And that is quite helpful for the better quality design of the IC chips for the hardware security. So now I would like to go to the more in-depth part. So now this is a power noise simulation technique I would like to talk about. So now the topic is quite changed. So that now we are I'm talking about the modeling methodology of the power noise on the IC chips. The CPS stands for the chip package system board. And here is a PCB model, and here's a package model. Okay, so here's a chip model. They're having the digital circuit of interest and also power converter models. The leakage leakage happening internally in the digital circuit of interest. And from the EM point of view, we are focusing on the power current flowing on the VDD and also on the VSS side of the circuit. So we simply need the power model, the power current models of the digital circuit of interest. In this case, the cryptographic engine is the most important. And the package model often simplified by the wiring or the bonding, or sometimes the line impedance governed by the inductance. And the PCB model, in this case, the RLGC, resistance, inductance, capacitance, and the conductance models. It's a distributed model. And we often have the lumped decap in between on the PCB board. And the chip itself can be simply represented by the chip capacitance and also the series impedance on the power delivery network. Those are passive models. And we need active models that stand for the power consumption currents of the circuits under the operation. This is a so-called CPS, chip package system board model. For the passive part, as I mentioned, the lumped or distributed components can be simulated or extracted and simulated with the existing simulators like a SPICE. And the frequency response of the impedance can be extracted by the simulation as shown on the blue curve on this chart, and that can match well with the measurements. Horizontal axis gives you the frequency of the interest, and the vertical axis gives you the impedance on that frequency. The impedance decreases by the capacitance and then increase again by the inductance and so forth. Those the resonating frequencies and those responses are well captured by the model. This is the passive part. But what we can do for the active part? This is the so-called chip power model. Sometimes we abbreviated it as a CPM. And this model has, again, two major parts. One is active part, power current model, and the other one is a passive part. Again, this is the passive part only within the chip. And the VDD stands for the part voltage side, the high side of the power delivery network, and the VSS is the ground side or returning side of the power delivery network. And the CPM, this is including the power delivery network with the multiple power current models. Power current models stands for the engines, digital circuits, I/O circuitry, those the circuits which consume the currents during the operations. And the passive part of the chip power model can be represented by the very dense linear network model, because on the chart on the left hand side, here is a device like a MOS device. Here is a gate electrode, source and drain electrodes, and the welds of the N-type over the P-type silicon substrate, for instance. And if we want to capture the passive part of the network, we need to see the technology profile, what kind of the impedance profile internally in the device. Those information can be given by the silicon foundry and then mapped to the dense network of the circuits. Power supply RC network means that the VDD side and the VSS side of the network. In this case, I just simply sketch the network just with the resistive material, but obviously we also need to include the capacitance specifically locally in each of the device. And the one important thing I would like to mention here is a substrate RC network is also needed for the chip level model. In the silicon substrate, those are resistive material, but different impurity type. That means we have junction capacitance between the N-type to the P-type, or P-type to the N-type, vice versa. For the P-type silicon, P channel and the N-channel MOSFETs. So those distributed capacitances need to be included in the substrate RC network. So nowadays, those models can be automatically extracted by using the tool provided by the EDA company. But we need to understand the models are comprised of the passive dense network, the passive components. For the active part, for instance, in the digital case, standard cell library often used, especially for the digital circuits and also for the cryptographic engines. We are using the NAND cell, inverter cell, and flip-flops, and many others. But those cells can be pre-characterized in terms of the power currents flowing through the gates. In the gate operations, sometimes the output is going to 0, and sometimes output is going to 1. The output value dependencies and also input value dependencies the input to the output relation can be represented by the truth table. But from the power current model perspective, we need to record the power current wave shapes for every combination of the input to the output. In addition, sometimes those current waves forms are created for the different set of the load capacitance. Load capacitance means the wiring capacitance seen from the output of the gate, and so forth. And moreover, the voltage variations, temperature variations, and the threshold voltage variations, so-called PVT variations, are also mapped in the power current wave shape, library. So those wave shapes can be pre-characterized beforehand, before the designing the big chip. Those are used for the later the simulation of the whole digital circuits. So the chip level model means the combination of the on-chip active parts, as I mentioned in the previous slide, with some gates like a NAND, inverter, and some others. Those gates are represented by the captured current model. So in this case, the current model stands for each of the gate. And those current models are connected to the resistive capacitive networks of which are included in the passive part of the model. And once again, sequence subset models are attached to the power grids models. So power delivery networks, all the gate components, and also sequence substrates are packed together to form a single big netlist of the digital circuit. This is a very general sketch, and that can be created for any kind of the digital circuits, including the cryptographic engines. So now the model often needs to be calibrated, actually, because as I showed you, the many different components are included in the model. That means there are many the parameters to be well managed to capture the proper power current. So how we can do this? One of the things we are doing here in Kobe that way, like this. We can set up the model for a quite simple circuit like DFF or a shift register. This shift register is composed by the DFFs. And the array of flip-flops can be implemented in a silicon die with a given technology like a 65 nanometer nodes. And then measurements were happening on that chip as a reference case. And the measurement results can calibrate the simulation results. Once we do this for the simple circuits, like the shift register array, as I mentioned, then that modeling environment can be reused for any kind of the circuits. And what measurements we can do? One of the technique shown here is on-chip monitor. This monitor can capture the wave shapes on the die, on the BDD side, and also BSS side. Full chip simulation can be calibrated by the on-chip measurements. The circuit itself can be quite simplified. It's a kind of the AD converter, very simplified version of the AD converter, and that can capture the voltage wave shapes seen on the BDD and also on the BSS side. Here's an example. In this case, here is a big digital circuit, including AES. This is one of the well-known cryptographic engine. And once the AES is operating, there are many noises happening, quite relevant to the operation of the AES. And on-chip monitor can capture some points over the die For instance, in this case, silicon substrate voltage can be captured. And also the core VSS side, ground side, return side of the AES circuit can also be captured by the OCM. The chart on the right hand showed you the measured wave shapes. The horizontal axis gives you the time, and the vertical axis gives you the measured voltage. So the voltage variation happening on the silicon substrate when the AES is operating. If you see, here are some ticks that are in line with the clock position, rising edge and falling edge. And quite similar wave shapes can be seen on the VSS. Because this substrate is always, in the case of the p-type substrate silicon device, those silicon substrate is tied up with the VSS side of the circuit. So the VSS sub is often be identical, almost identical to the noise seen on the VSS. But anyway, the measurements can give you the idea of what kind of noise happening during the operation of the circuit. In detail, in this case, the VDD side and the VSS side of the AES core are simulated by using the chip package system board models and compared with the measurements done by the on-chip monitor. The size and the wave shapes are almost equivalent. Of course, there are some difference, especially on the VSS case in this particular example. I would say in this case that silicon substrate model is not well calibrated. But anyway, those are the idea of how that consistency can be checked by using the on-chip monitor and also the simulation using the chip package system connected model. Once we get the simulation technique, that can be applicable for the side channel leakage analysis. Here, I just give some notes on what's the cryptographic engines we may have in the world. There are two big categories. One is a public key crypto, and the other one is a private key crypto. Now, public key crypto, which is sometimes we call it as asymmetric key types of the cryptographic engine. In this case, different key is used for the encryption and decryption. And sometimes those keys are the pair of the keys for the public and the private domains. This means the public key means everyone can see, but private key is only the one who wants to encrypt the data, for instance. In this usage model, the public key crypto, if I encrypt some data, everyone can decrypt the data by the public key, but everyone doesn't know what's the private key I'm using. In this case, it makes sure by nature, it makes sure that this data, this decrypted by the people, that those data are coming from my side because I encrypted. This usage model is quite useful for the case where the digital signature are needed, because that the data, who creates the data is sometimes very important. So the public key crypto is a kind of such the asymmetric usage model of in the field of the security. I think you can see the more detailed explanation in the textbook. On the other hand, there are another group called private key crypto. In this case, the symmetric key usage model. In this case, a single private key is used for both encryption and decryption. This means that myself and you are sharing a specific key between us. So if I encrypt my data, you can decrypt the same data with the same key. In this case, the key needs to be well managed by myself and you, and not disclosed to the other people outside of us. This is the scenario of the private key. And there are well-known algorithm in each of the category. Elliptic curved type of the algorithm and also RSA belonging to the public key crypto. AES, this is one of the key device in my talk, is belonging to the private key crypto. The big difference we see between the private key and public key crypto in terms of the IC chip designs. Often for the public key crypto, we need to have the thousands of clock cycles to complete the encryption or decryption operation. Because of the many clock cycles are needed for the scalar multiplication, point doubling, point addition. Those are the fundamental, the arithmetic processing units used in the public key algorithm. Once again, for the public key crypto, we need more than thousands clock cycles to complete. On the other hand, for the private key crypto, like AES, depending on the design, but often only 10 or 12, 10 to the 20 clock cycles are used for a single encryption or decryption. So very efficiently, data can be encrypted or decrypted by using the private key crypto. So in general, in general field, those two are combined together in the system. But obviously, the efficiency is always a key. In that case, the AES is used for many different situations. So we need to protect the AES from the attackers. This is the general sketch of the architecture of the AES cryptographic engine. I don't go into the detail of the algorithms, but from the architectural point of view, here is a data path which implement or realize the permutation and the substitutions in the data flow of the AES. This is a very key part. And also, we have the key shuffling part on the right-hand side. And those two are combined together to create the encrypted version of the data. In this case, the plain text is input, and the output is decrypted data. By using this data path, and normally this is a kind of the loop architecture. That means first line, first processing, and the data is coming back to the input again, and the second, and the third, and so forth. Normally often that's these types of the architecture uses 12 clock cycles or 12 loops internally in the processing of the AES. Now, I would like to show you what's the leakage happening in this AES. Actually, in the AES, if attacker try to correlate the output data, encrypt the data with the input plain text, they will not see anything. At this moment, AES is quite powerful and quite strong. Therefore, the function between the D out and the D in will not be disclosed or resolved by an attacker. But if an attacker can measure the EM waves or power currents, then the attacker may see some correlations between the internal operation of the AES with the collected power currents. This is the key thing here. Once you implement your the cryptographic algorithms, but the chip may give you the way to extract some secret information just by measuring the electromagnetic waves. Sometimes we call it side channel leakage. Side channel means that main channel means the data path. But side channel, power current wave shapes or EM wave shapes, or sometimes the delay of the processing, and so forth. The different things from the main path can be defined as a side channel. Examples. In the operation of the AES with a different plain text, we see the difference in the power current. Those power current are depending on the input plain text and potentially depending on the internal secret key bytes. If we, in this case, this is a simulation version, by the way, but in the measurement, we may see the voltage drop happening on the board or the size of the EM radiation from the board. The horizontal axis gives you the Hamming distance. I will show you later anyway. The horizontal axis, Hamming distance, and the vertical axis gives you the voltage drop because of the current consumed by the AES processing. We see the obvious correlation. Larger Hamming distance, larger voltage drop. So this linear relationship can be the source of the leakage. What's the Hamming distance in this case? Data register, if you see. In the very last round of the AES, by definition, the key shuffling will not be mixed. And, the mixed column will not happen. So the very final rounds, one of the processing stage will be eliminated. So simplification will be happening for the attacker. And the data register will change its value from the previous round to the last round. In this case, how many bits changed in the data register can be a kind of the metric of the attacker can use. Those are how many bits shifted can be measured by the Hamming distance by definition. So this obvious relationship may make some leakage and may make some correlations to the internal secret key byte. Now, this is the actual attacker, what the attacker can do. Horizontal axis gives you the number of traces. This means the number of the different plain text given to the AES unit. And vertical axis gives you the correlation with the secret key. Of course, the attacker will not see what's the key inside. But after the analysis, the most strong one among the candidate can be determined. Because one more thing, each of the AES core has the byte parallel byte type of the analysis. That means the one byte stands for the 256 different numbers. So among the 256 numbers, one of them can have the highest correlation with the Hamming distance or the voltage drops or the EM strengths measured outside of the die. In this particular case, among the 256 different candidates, only one of them has a different trend in terms of the correlation with the measured numbers, like a voltage drop. Once we determine the one especially different from the others, this can be the potential key number. And those will be repeated for the 16 different bytes in the operation of the AES. Because that the AES algorithm or AES architecture are well known by the attacker can assume some models like this. And finally, the horizontal axis gives you the number of traces, and the vertical axis gives you the number of analyzed key bytes. This means how analyzed the number of the keys that can be specified after the correlation analysis shown on the left-hand side. If we determine all the 16 key bytes, that means the complete set of the secret key can be disclosed, or the attacker can now understand, or the attacker can now decrypt all the encrypted data. Unfortunately, in this case. So the horizontal axis gives you the number of traces, as I mentioned. The vertical axis gives you the number of analyzed key bytes. The trends are different among different designs. In this case, the red circle and the cross and the square, those stands for the different design style happening on the AES. I don't go into the detail, but the different design styles will give you the different the trends of the leakage observed by the attacker. In this case, the composite design is better than the PPRM design because the attacker needs a larger number of the traces to determine or to analyze the secret key bytes. This is a very important message. You can design in the proper way, try to eliminate the leakage, but the attacker can make the measurements for big number of traces, like in this case 10,000, but easily that can be increased to the 1 million or even 1 billion. Attacker had, once again, they have the another the freedom. How many traces you can capture? If they have the big data server, they can easily handle the millions of the traces and to make the correlation shown on the left. This is another source. Nowadays, one of the metric of the strength of the tolerance of the AES core is the number of traces. How many traces you need to assume the secret key byte? Those needs to be more than the 10 millions or even on billions. From that perspective, how we can simulate, how we can design the chip before being attacked by the adversary. So we need to make the simulation for different plain text given to the cryptographic engine under the design. That means we need to have the very efficient way of the simulations. CPM can be one of the technique providing you the methodology because all the currents are pre-recorded in each of the gate, as I mentioned. That means the different plain text means a different set of the current wave shapes. And those current shapes will be combined together and interact or interfere or interact with the passive model on the chip and also on the package and the board. Those interactions will give you the wave shapes, and then that you can apply the analysis as in the attacker way. In this case, one simple idea I can show you is that the PDM model, passive model, can be reused for the different plain text given to the cryptographic engine. That means the separation can be applied to the analysis. Step 1, full chip power delivery network modeling. This means the passive part of the model can be extracted in the step 1. And the step 2 is the power models for the cryptographic engine like AES. Two models can now be decoupled. That means we can reuse the passive part of the model for the different active models. This will accelerate the modeling time. In the case 1, the private key, as I described in the previous slides for the AES, the power noise waveforms can be simulated for the different plain text. Potentially in the surveillance of the architecture or surveillance of the circuit techniques, typically 10,000 the simulation cycles are sufficient. Not exactly sufficient, but you can use those simulation results to select which way we should go. Sometimes we may use a different place and route of the gate in the AES, or sometimes we may insert some additional capacitance or the gates in the AES engine. Many tricks have been reported in the worldwide, and those can be explored in the design phase by using the 10,000 different plain text given to the AES with this simulation technique. I will not go into the detail, but those ideas can also be useful for the public key crypto. Once we create the passive models that can be reused for the different plain text for the AES case and the different clock cycles for the public key case. As I mentioned, that for the public key case, that we need more than thousands of clock cycles to complete the encryption or decryption, so that we need to split the model into the different clock cycles. And once again, the path model can be reused. And those are implemented in the simulation flow shown here. In the left-hand side, full chip PDM modeling, as I mentioned, that the reusable model can be created and logic cells can be characterized beforehand. And then core level power modeling can be done on each of the different plain text given to the AES core in the case of the private key, for instance. And those are combined together, and then simulation can be done with the SPI simulation if you want to see the physical wave shapes on the chip. Sometimes those models can be combined together with the power management control circuits, like power converters, DC-DC converters, with the combination to the package model and the board model with the different capacitance, different decoupling circuits. Okay, I would like to show you some examples from the perspective of the simulation technique on the side channel leakage. Here is again the AES core in the 130 nanometer CMOS process in this case, and the evaluation board and the package are all designed by ourselves and extracted the models. In the private key crypto of using the AES encryption engines, having the 34 kilogates and operating frequency at bit small frequency like a 34 megahertz in this case. And the power noise on the VDD can be simulated by using a CPS simulation with a different plain text for the set of 1500 in this case. And the last round of the encryption, the voltage wave shapes are captured, and see here is a difference among the voltage wave shapes with a different plain text because of the Hamming distance different in each of the input text. as I showed you in the previous chart. So once we got this simulation results, we may apply the correlation power analysis as the attacker is doing. And those can be doable as a simulation before going to the tape out, before going to the manufacturing of the die. Here are some the simulation cost. It's doable. I would say it's a one day is enough for the simulation. And what's acceleration? So the decoupled approach that use the passive part of the CPM, passive part of the model, be used for the different active part of the models. Cost can be compared. The passive part normally takes a very, very long time because the dense RLC network needs to be extracted from the die, but that can be done only once. And the active part, this is the kind of the combination of the active current models that can be quite fast in comparison to the extraction of the passive part model. And the reusable approach, the cost is quite reduced. And this proposed flow can accelerate the process or the design of the chip having the cryptographic engines. And many different type of the techniques can be applied on the design to increase the number of traces needed by the attacker to extract some important information. So here is the example. I think this should be the last slide of my presentation today. The horizontal axis gives you the number of traces, once again, and the number one is the rank of the guessed key bytes. In this case, the number one rank is most relevant the key bytes to the input wave shapes simulated or by the measurements. After the 2700 cases, the on-chip VDD wave shapes give you all the key bytes in this case. So that means attacker needs to have the 2700 different wave shapes to access the key. This is not the best design, I would say, but the simulation can tell you how that design is good or not. And onboard connector quite similarly give you the necessity of these 1300 different plain text. And the measurements, in this case, 38. So those three are almost identical or almost the same. So that means the simulation is good quality or good the accuracy in comparison to the silicon measurements. So side channel attack can be simulated by using the efficient simulation techniques if you have. And those techniques can be applicable for the exploration of the design techniques to hide the leakage on the AES core, for instance. So now I would like to conclude my presentation today. So we have quite relevant disciplines, as I mentioned, between the EMC and HWS, hardware security research fields. The knowledge, in this case, that EMC emission immunity is quite relevant and quite complementary for the emission, for the device response, and immunity is normally on the system characteristics. And those ideas or those analysis or those knowledge can be wisely used for the design of the electronic systems towards high security and safety. And just one example, I showed you the techniques called the CPS, chip package system models used in the power node simulation that can accelerate the exploration of the chip of the CPA correlated power analysis on the AES cores by design or in the design phase. Those techniques can be play a key role in the design of the security systems or security circuits, therefore suppressing the side channel information leakage through the power supply and the EM channels. There are many other trials, many other activities on the design methodologies, research activities on the design methodologies on the better hardware security and hardware security in the world. But this is one of the approach I explained. Okay, so those are key differences, and that's it. So thank you very much for your kind listening to my presentation today.